The fetal skeleton starts developing soon after gastrulation, which is when the trilaminar disc with ectoderm, mesoderm, and endoderm layers are formed. There are two parts of the skeleton: the axioskeleton, which includes the bones in the skull, the vertebrae, the rib cage, and the sternum, and the appendicular skeleton, comprising of the pelvic and shoulder girdle, as well as the bones in the limbs. The bones in the axioskeleton mostly derive from the mesoderm layer, except for some bones in the skull which come from the ectoderm. And all of the bones in the appendicular skeleton derive from the mesoderm. During week 3, the embryo transitions from a flat organism to a more tubular creature, by folding along its longitudinal and lateral axes. At the same time, a solid rod of mesoderm called the notochord forms on the midline of the embryo. Above the notochord, the ectoderm invaginates to form the neural tube, which is an early precursor for the central nervous system. This is the embryo's first symmetry axis, and the mesoderm on either side of the neural tube differentiate into 3 distinct portions. Immediately flanking the neural tube, there's the paraxial mesoderm. Next, there's the intermediate mesoderm, and finally the lateral plate mesoderm. The intermediate mesoderm gives rise to the urinary and genital systems, while the paraxial mesoderm and lateral plate mesoderm work together to give rise to most of the bones and muscles in our body. Now, the first step in skeletal muscle development is when paraxial mesoderm segments into blocks of mesodermal tissue called somites, which are made up of lots of cube-shaped cells. Next, the somites divide into 3 different cell populations: the sclerotome, which forms the vertebrae, the rib cage, and the lower part of the occipital bone, the dermatome, which forms the skin of the back, and the myotome, which forms the back, limb, and intercostal muscles. Meanwhile, lateral plate mesoderm splits into parietal mesoderm and visceral mesoderm layers. The parietal mesoderm forms the early limb buds, as well as the bones of the pelvic and shoulder girdle, and the sternum, while the visceral mesoderm helps form organs like the heart, lungs, and organs in the gastrointestinal tract. So the axioskeleton derives mainly from paraxial and lateral plate mesoderm cells. But in the head region, another group of cells derived from the ectoderm layer, called neural crest cells, contributes to the development of the skull. Before they develop into bone, all these different kinds of cells first transform into multipotent mesenchymal cells, through a process called epithelial to mesenchymal transition. The resulting mesenchymal cells have special properties, like the ability to migrate to different locations and give rise to different organs and tissues in our body, including bones. Now, from here, there are 2 ways that fetal bones can form. First, there's endochondral ossification, where mesenchymal cells first differentiate into chondrocytes that build a hyaline cartilage model, which then turns into bone. When that happens, the center of this cartilage model is the primary ossification center, and blood vessels enter it, bringing nutrients and osteoblast cells which help bone form, B for build, as well as osteoclast cells that collapse bone, C for collapse. The osteoblasts replace the chondrocytes at the primary ossification center and start to replace the cartilage with bone. As the bones grow thicker and more sturdy, osteoclasts start to chomp away in the middle of the bone, making it more porous, and this is how bone marrow appears. Most of the bones in our body form through endochondral ossification, except for the clavicles and the bones in the skull like the parietal and frontal bones, as well as the maxilla, mandible, and nasal bones and parts of the temporal and occipital bones. These exceptions form through intramembranous ossification, which is when mesenchymal cells differentiate into osteoblast cells which create the primary ossification center and start building bone without any cartilage model. As before, blood vessels reach the center of the primary ossification center, which already has osteoblasts, and starts bringing nutrients. Alright, now let's start at the very top and take a look at the development of the skull. The skull has 2 main parts: the neurocranium, which is the hard shell protecting the brain, and the viscerocranium, which makes up the structures underlying the face. The neurocranium is itself divided into 2 parts. First, there's the membranous neurocranium, which forms through intramembranous ossification, and makes up the flat bones of the skull. These flat bones surround the brain, and you can think of a protective helmet. Anteriorly, there's the frontal bones, above the parietal bones, posteriorly a part of the parietal bones and the occipital bone, and laterally a special spot where the parietal, occipital, and temporal bones meet, like 3 old friends. Then there's the cartilaginous neurocranium, or the chondrocranium, which forms through endochondral ossification and gives rise to the base of the skull, or the bony floor underneath the brain. The chondrocranium accounts for the rest of the occipital and the temporal bones, as well as the sphenoid and the ethmoid bone. The viscerocranium arises from the first of the pharyngeal arches, which are 5 paired bars of mesoderm that arch toward one another along the midline of the embryo. These arches have a core of mesenchymal cells which originate as neural crest cells. As far as facial bones go, the first pharyngeal arch forms the upper and lower jawbone, as well as the cheekbones and the temples of the skull. To go back to the helmet analogy, the viscerocranium would make up the face guard protecting our mouth and nose from damage. And this face guard is slightly curved, to remind you that the bones come from the first pharyngeal arch. When a baby's born, the skull bones are not fused, and it looks a bit like a jigsaw puzzle where the pieces haven't quite snapped together. Between the bone plates, there are long, narrow, fibrous sutures that hold the skull together. Wide openings called fontanelles exist at the points where more than 2 bones come into contact. There's 6 of them in total, 2 on either side, 2 larger ones on top, the anterior fontanelle between the parietal and frontal bones, and the posterior fontanelle between the occipital and parietal bones. These sutures and fontanelles provide the skull with a tiny amount of flexibility, which makes it easier for the large head to squeeze through the vaginal canal during childbirth. After the baby's born, the fontanelles close up one by one. The last one to close is the anterior fontanelle, and it's often referred to as the soft spot on a baby's head. It closes around 18 months. During week 4 of development, the spinal vertebrae develop, and it happens when the somites undergo a process called resegmentation. First, each somite separates into 2 populations of cells, a rostral or top population, and a caudal or bottom group. Next, these 2 populations of cells separate, and the bottom population of one somite fuses with the top population of the ensuing somite. This gives rise to new segments of tissue formed by cell populations deriving from two separate adjacent somites. The sclerotome cells in these segments surround the notochord and spinal cord, and they transform into mesenchymal cells and give rise to the vertebrae through endochondral ossification. As the vertebrae take shape, the neural tube develops into the spinal cord, from which spinal nerves emerge through the spaces between the vertebrae. In front of the spinal cord, though, the bodies of the vertebrae grow and make the notochord degenerate, for the most part. Between the vertebrae, the notochord persists as the nucleus pulposus of the intervertebral discs. During week 5, small clusters of mesenchymal cells called costal processes emerge from the lateral sides of each vertebrae. In the thoracic region, these processes grow really long and form the ribs. Finally, the sternum develops from the parietal mesoderm layer in the anterior body wall of the embryo. Here, the parietal mesoderm organizes as a pair of vertically oriented cartilaginous bars on either side of the midline, which eventually fuse and differentiate into the three parts of the sternum: the broad manubrium at the top, the main body of the sternum, and the small xiphoid process at the bottom. Alright, as a quick recap, the axioskeleton arises from mesodermal and neural crest cells, which turn into mesenchymal cells. Mesenchymal cells then give rise to bone, either through endochondral ossification or through intramembranous ossification. The bones and cartilage of the spinal vertebrae, as well as the rib cage, derive from the somitic sclerotome. The sternum develops separately from the rest of the rib cage, emerging from parietal mesoderm in the embryo's ventral body wall.